Hello everyone and welcome to another week of physics. Today we are going to start chapter 3, Newton's Laws. Newton's Laws are something that you've probably been familiarized with already, whether you know it or not. They're actually encompassed in several simple phrases that are used all the time by people, and you'll probably recognize them as we begin to define them. But Newton's laws are incredibly important. They're some of the greatest discoveries in physics, and it's not necessarily that any of them were new, but being able to put it down in words and see that it works that way every time really helped establish physical laws. And as we get further into this chapter, when we see Newton's second law, particularly the equation for Newton's second law, may be one of the most important equations in all of physics. So let's get to it. So really the whole idea behind this chapter is what causes accelerations. We spent all of last chapter studying motion, and we saw position, velocity, and acceleration, and how they were related to each other. And while we answered questions of what's going to happen in certain situations whenever you accelerate an object, we never really addressed why or what causes accelerations. And the answer is forces, and that's really going to be what we talk about all day long. So, in 1687, Isaac Newton published Principia, which has a much longer name. It's usually shortened to Principia, and you'll see why. It's really the Philosophiae Naturalis Principia Mathematica, or sort of on the natural philosophy of the principles of math, something along those lines. I don't know. I don't speak Latin too well. But anyway, he outlined his rules for motion, the so-called Newton's laws within Principia, and those things still hold up today, except for very extreme cases that have only been discovered rather recently, actually. And we'll see in our studies that, yeah, they still work for almost everything, except these two special cases, and they are truly extreme situations. One of those is when objects approach the speed of light. At this point, Einstein's theory of relativity takes over, and Newton's laws sort of break down. The other situation in which these laws no longer hold are for quantum physics, when you start studying things that are very, very tiny. When you get onto the level of things smaller than molecules, when you're starting to study individual atoms, the rules of Newton's laws don't really hold up. An electron does not orbit a proton in the ways you would expect based on Newton's laws. But that's a whole other topic for another day, not within this survey of physics course even. But without further ado, let's get to Newton's laws. So, the first law, Newton's first law says, an object at rest tends to remain at rest. An object in motion tends to remain in motion in a straight line unless acted upon by an outside force. And there's that word force. It's going to pop up in every single one of Newton's laws. That's why I've underlined it. Force really is our focus today. The first law is also referred to as the law of inertia. And you guys might use inertia in your daily vernacular, the words you use in casual conversation. And inertia is tied closely to this. Inertia has to do with an object's ability to resist change in motion. If you have a lot of inertia, it is hard to get you moving, or alternatively, to stop you if you are already moving. If you don't have much inertia, it's very easy to get you moving, and it's very easy to stop that motion once it has begun. Newton's second law says the acceleration of an object is proportional to the net force upon the object and inversely proportional to the mass of the object. And this is starting to get back to that word acceleration and what causes them. We still haven't completely, detailed that just yet, but we're seeing the relations between them. We know that acceleration is proportional to the net force. And there's that word force. And it's inversely proportional to the mass. So what does that mean? Well, we're going to be talking about directly proportional and inversely proportional throughout this class as we look at the relationship between objects. But to put it simply, if things are proportional, when one goes up, the other goes up. If you add more force, if you push harder, you get more acceleration. If you push less hard, you get less acceleration. That's directly proportional. One goes up, the other goes up. Or if one goes down, the other goes down. The opposite of that is inversely proportional. So if you have more mass, we use the letter M for mass, as we'll talk about more today. If you have more mass, it's harder to accelerate you. More mass means your acceleration is going to be less. Or if you have less mass, it's more easy to accelerate you. Less mass means that acceleration can go up. Again, a harder push, more acceleration. More mass means harder to accelerate. That is Newton's second law summarized. And finally, let's get to the third law. Newton's third law. For every force, and there that word is again, force, there is an equal force in the opposite direction. That is, they always come in pairs. If there is one force, there must be a second force. Forces always come in pairs, and they're always equal and opposite. And I like to highlight that this is not action-reaction, this is action-reaction. It is not cause and effect. And to give you just a quick example of that, if you kick a bowling ball and it moves, that is cause and effect. You kicked it, it moved, cause, effect. Newton's third law, rather, would be that if you kick a bowling ball, ouch, that's going to hurt. The bowling ball kicks back. You apply a force to the bowling ball in one direction, it applies a force to you in the opposite direction. And the best way to think about this is just your everyday action. If I want to jump up, I push my legs downwards. I push into the ground pushes on me and causes me to go up into the air. Or if you're in a swimming pool and you kick off against the side of the pool, you're pushing against the side of the pool. The side of the pool then is what pushes you forward. Or if you're driving your car, the friction between your tires is what causes you to move, but your tires push backwards, and then the ground pushes your car forwards. That is Newton's third law. It is action and reaction. And it is, in my opinion, the coolest, but also the trickiest of Newton's three laws. So we're going to go ahead and pause there, and we will get into some examples of forces. Obviously, they're central to this chapter. And we've now established Newton's laws. Now let's establish an idea of forces so we can start talking about them in more detail.